You know, with every single breath you take, there's this incredibly complex and beautiful process that unfolds, powering every last cell in your body. Today, we're diving deep into the science behind that miracle, pulmonary gas exchange.
All right, just a quick heads up before we jump in. This is going to be a pretty advanced explainer. We're getting into some detailed physiology here, and we're kind of assuming you've got the basics down. If you're looking for a more introductory take, we've got you covered in our previous explainer on this. So, here's the game plan. We'll start with the big picture, the grand design. Then, we're going to follow a single molecule of oxygen on its amazing journey from your lungs all the way to your tissues. And after that, we'll track a molecule of carbon dioxide on its trip back home. Let's get into it.
Okay, so before we put on our microscopic goggles and zoom way in, let's just lay the groundwork. There are three fundamental pillars that make this entire system work. It's this beautiful dance between physics and biology.
Think of it like a three-legged stool. First, you need ventilation. That's just the mechanics, the physical act of moving air in and out. Then you have diffusion, which is pure physics, gases just moving on their own across membranes. And finally, perfusion. That's your heart and blood vessels doing their job as the ultimate delivery service. All three have to be working in perfect harmony, or the whole thing falls apart.
All right, now let's zoom in. We're going right to the heart of the action, the alveoli. These are these millions of teeny tiny little air sacs where the outside world, the air you just breathed in, gets incredibly close to your internal world, your bloodstream. Now, to really get what happens next, we have to talk about the engine that drives this entire process, partial pressure. It's a really simple, elegant law of physics. It basically says a gas will always move from an area where its pressure is high to an area where its pressure is low. It's like water flowing downhill. No energy needed from your body whatsoever. And check this out. This is a perfect example. The partial pressure of oxygen in the air you just brought into your lungs is about 100, but in the deoxygenated blood that's just arriving at the lungs, it's only 40. That creates this massive downhill slide, and the oxygen just tumbles completely on its own from the air sacs right into your blood.
So what makes this happen so incredibly fast? Well, it's the barrier itself. It is ridiculously thin. The wall of the air sac and the wall of the tiny blood vessel, the capillary, are basically fused together. This creates a membrane that's only about 1 micron thick. That's 1,000th of a millimeter. It is an amazing piece of biological engineering, and it's built for one thing: speed.
Okay, so the oxygen is officially in the bloodstream. Awesome. But there's a catch. Oxygen doesn't really like to dissolve in the watery plasma of your blood. In fact, only about 2% of it can travel that way. For the other 98%, the body needs a dedicated ride, and that's where the hemoglobin shuttle comes in.
Meet hemoglobin. This is a super sophisticated protein that's packed into every single one of your red blood cells. And as this quote says, it's not just some dumb taxi. It's more like a smart car. It literally changes its behavior depending on where it is in the body, making sure it grabs oxygen in the lungs and drops it off exactly where it needs to go.
The way it does this is through a genius mechanism called cooperative binding. So here's how it works. Getting that first oxygen molecule to latch on is actually kind of tough. But once it does, it causes the whole hemoglobin protein to change its shape. This new shape makes it way easier for the second, third, and fourth oxygen molecules to jump on board. It's like a chain reaction that ensures hemoglobin loads up to full capacity in the oxygen-rich lungs.
And just how good is this system? Well, get this. In every 100 milliliters of blood leaving your lungs, that's less than half a cup, hemoglobin is carrying a full 20 milliliters of oxygen. That transport capacity is absolutely what allows us to be the active, high-energy beings we are. So, our red blood cell, now fully loaded with oxygen, has traveled through the arteries and arrived at a place that's working hard, like a muscle you're using. The mission is now to unload the precious cargo. But how in the world does hemoglobin know that this is the right stop?
Well, once again, the answer is partial pressures. But notice how the tables have completely turned here. In these active tissues, oxygen is being used up, so its partial pressure is really low, less than 40. At the same time, the tissue is producing carbon dioxide as waste, so its partial pressure is high. This new pressure difference is what starts the process of oxygen moving out of the blood and CO2 moving in.
But wait, it gets even more clever. The waste products themselves are the trigger for oxygen release. It's brilliant. As CO2 seeps into the red blood cell, it creates hydrogen ions. Now, both the CO2 and these hydrogen ions latch onto the hemoglobin molecule, but not where the oxygen is. This binding forces another shape change, which basically lowers hemoglobin's desire to hold on to oxygen, and it gets kicked off right where the tissues are screaming for it.
You know what's fascinating? Even when you're just sitting around, your body doesn't use all the oxygen it's carrying. If you look at this chart, the venous blood heading back to the lungs is still about 75% full of oxygen. This is your body's safety net, a huge reserve that's ready to go the second you start exercising or your oxygen demand suddenly goes way up.
All right, oxygen delivered. Job done, right? Not so fast. Now we have to deal with the trash. The carbon dioxide molecule has just entered the blood, and believe it or not, its journey back to the lungs is even more complicated than oxygen's trip out. So how does the blood manage this waste product? I mean, with oxygen, it was pretty straightforward, right? It just hopped on hemoglobin. But for CO2, the body uses this really complex, multi-part strategy. Take a look at this. Only a tiny bit, about 7%, just dissolves in the blood. Another 23% or so does bind to hemoglobin. But the overwhelming majority, a full 70%, gets converted into a completely different molecule for the trip. It travels as something called bicarbonate ions.
And this is where the red blood cell shows its genius again. Inside, it has this enzyme called carbonic anhydrase. This little guy is the unsung hero. It takes CO2 and water and converts it to bicarbonate at a blistering pace, literally thousands of times faster than what happened otherwise. It effectively turns every red blood cell into a tiny, hyper-efficient CO2 processing factory.
So we've seen just how elegant and efficient this whole system is. It's this cascade of perfectly balanced chemical and physical reactions. But, like any finely tuned machine, that perfection also makes it incredibly fragile.
And of course, just a quick disclaimer here. The information that's coming up is for educational purposes only. It is not medical advice. Please always talk to a healthcare professional about any medical concerns you might have. Now we can see how things can go wrong. Remember that super thin diffusion distance we talked about? Well, in pulmonary edema, fluid fills the lungs, making that distance bigger and slowing everything down. With emphysema, the walls of the alveoli get destroyed, which drastically reduces the surface area available for gas exchange. And if you go to high altitude, the partial pressure of oxygen in the air itself is just lower, which weakens the very engine that drives this whole process.
Okay, so let's boil this all down. What are the 5 big takeaways? First, the whole show is run by simple physics. Gases moving down pressure gradients. Second, the lung's architecture is built for speed with that razor-thin barrier. Third, hemoglobin is a smart molecule that uses cooperative binding to load up efficiently. 4, the body's own waste products cleverly trigger oxygen delivery right where it's needed. And finally, 5, most CO2 travels back in disguise as bicarbonate.
And the most incredible part? This entire unbelievably intricate life-sustaining cascade just happens. Silently, automatically, with every single breath you take, over 20,000 times a day. The whole system is built on pressure, which kind of leaves you with a final thought, doesn't it? What happens when that pressure changes?